a fantastic kinetic artist, George Rickey.
Thanks for all taking the time to come, and I'd like to really make this a conversation about bearings, about art, about moving art, about how we get from one place to another with our projects. And I've had a chance to chat with a few people. I was lucky enough to be able to take a few minutes in Royce's studio yesterday and got to see some really great bearing applications in kinetic sculpture. So I really want people to jump in, throw out questions, and direct me in directions you want me to go. Having said that, what I basically thought I would do is spend a few minutes talking about who I am and why I'm here, and from that jump down to a very basic Bearing Basics 101. Just talk a little bit about bearings, what they are, why they exist. I've got some fun samples to pass around. From there, we'll talk a little bit about how this might translate into what factors might be in play when you're thinking about sculpture. What kind of movements there are, what kind of conditions there are, what kinds of loads you might be looking at in your projects. From there, we'll talk a little bit about bearing selection, how you choose a bearing for a particular application. And then actually some things that you should be really careful about in your bearing designs. And this is where it would be great to have experienced sculptors chime in with what you've found, because hands-on experience is really the best kind. And then from there, we'll move on to a little bit about my association with and my company's association with the sculptor George Rickey, and then talk about your sculptures and anything else you want to talk about. So that's the general plan for today. So let me talk about why me. I grew up in the bearing business. My father started my company in upstate New York 63 years ago. I grew up with the company. I was a teacher in Boston, and 25 years ago I moved back to the Albany, New York area, where my business is actually in Troy, New York, and joined my dad in the business. My brother and I now run the business as a second-generation independent distributor. But what does that have to do with me being here today? My sister-in-law is a sculptress and a student here, and she had Edie Dillon, and she had a sculpture that she was trying to figure out how to turn a little better than it was turning, and she said, aha, I know the person to talk to about bearings. So she contacted me, and you have to understand that as the owner of a bearing company, it's usually a major conversation stopper at a party. You know, what do you do? Well, I sell bearings, and either people don't know what a bearing is. In fact, let's start from the very beginning here. Most people think that bearings are steel balls. So when you talk to the general public, and everybody says, oh, you sell ball bearings, well, it's like, well, how much can you do taking steel balls and selling them? What do you do? Do you sell them by the pound? Is it like coffee that you have dispensers and, you know? So it's usually a conversation stopper, but when Edie came to me, or talked to Cindy, and then said, man, it would be great for you to talk to the sculptors in Prescott. And of course, since usually the conversation stopped when I say I'm a bearing distributor, and all of a sudden somebody wanted me to talk about it, it was like, how could I not take the chance to do that? Now, what I am is somebody who's been running a bearing business for 25 years. I know a fair amount about bearings. What I am not is a mechanical engineer. So if there are any mechanical engineers in the audience, I'd kind of appreciate it if you'd leave, because it's going to make me look really bad. But no, I am not a mechanical engineer. I'm also not an artist. So really what I can do is talk about bearings and talk about how the world of kinetic sculpture might be opened up through the use of bearings. What I can't really talk about necessarily is technical aspects of design. In fact, George Rickey had a mechanical engineering professor at RPI as a consultant for him, and this guy was smart. Not only did he do great designs, but he took his pay in sculptures. So he owns, I would say, about 15 George Rickey sculptures, which are now worth a fortune. But anyway, so I could give you some guidelines, but I would say probably for a kinetic sculptor, the sculptor's best friend is an engineer of some sort. Or another sculptor who has already done this stuff and has some really good hands-on experience. So let's talk about the basic of bearings. Why bearings? So when you're talking about movement, the enemy of movement is friction. Friction is what keeps things from moving. So what we want to do in getting things to move is to overcome friction. That's the basis of all kinds of bearings, but not just bearings. When you go on a table and you spin a top, there's a reason that the point of the top is a point and not a box that you're trying to spin. Sure, you can spin a box, but when you spin a top, it spins because you've cut down, instead of having a whole plane of contact between the object and to inhibit its spinning, you have a single point. That's the basic concept that happens with particularly a ball bearing. But there, besides just talking about overcoming friction, there are a couple different ways that there are different loads that are put on objects when you're trying to overcome the friction. So we're going to be talking primarily about two different kinds of loads today. The first is a radial load, and I think the best way to think about a radial load is a ceiling fan. And see if, whoops. And a radial load is, if this is the axis, we call it a shaft in the industry. If this is the shaft, then the radial load are the basic forces of rotation. That's what we generally think about when we think about overcoming friction with a bearing, and that's called radial load. However, there's a second kind of load that needs to be considered, and that's either called axial load or thrust load. And the thrust load is the perpendicular load. While a radial load would be the spinning of a ceiling fan, the thrust load could be my weight as I'm trying to spin on the floor. And so, here, let's see if I can do this without making a fool of myself. My weight is the force down that provides the thrust load that needs to be overcome with some kind of bearing. Now, I happened to mention Royce and being at his workshop yesterday. He had a beautiful sculpture that on the top had a radial bearing and on the bottom had a thrust bearing, because the sculpture turns on a single shaft. It's got cup formations that I presume catch the wind, but it probably weighs 50 pounds, 75 pounds, I don't know what it weighs, of the weight on the base, and so that all of that weight is thrust load. There are places where thrust load is actually created by more than just weight, but thrust is something to consider. But so when we're talking about bearings, we talk about radial bearings, we talk about thrust bearings. Now, the other thing that's really good to consider, and I think it's worth talking about a little bit here, and I realize I'm going to have to kind of keep my eye on the watch so I don't keep you guys too long, is kinds of motion. Because, again, when we're talking about spinning motion, rotary motion, that's the first kind of motion that people think about. And in fact, it's very common motion. And it's very common motion in kinetic sculptures. So here is a basic example of rotational rotary motion. But there are also a lot of other kinds of motion that certainly could be incorporated into machinery, into everyday life applications, into sculptures. One motion is linear motion. So rather than having a fixed bearing spinning, if you had something that was easily sliding up and down the shaft, or you turn this sideways across a shaft, now there are a ton of industrial applications for linear motion. When you have a milling machine and you're bringing a piece of a product into the milling machine, and it has to be very carefully indexed so that you're drilling the same holes, off it goes, the next one comes in. That's done on linear motion equipment. And so there's all kinds of applications for linear motion equipment. But certainly linear motion is a motion worth considering when you're looking at doing sculpture. I have a sample here, and I'll kind of pass these different samples around so people can look at them, play with them, and pass them on. But just this is a little piece of shafting. These red plastic cups just keep the bearing from falling off the shaft. But this particular linear bearing moves across the shaft, but it also has the ability to do rotation. So it's doing two kinds of motion. It can do linear motion, and it can do rotational motion. So these are kind of fun to play around with. I'll start one on that side of the room. Other kinds of motion worth thinking about is, and chime in if you could think of them, but a swivel kind of motion. So, these kinds of bearings are actually called rod end bearings. And rod end bearings have a particular industrial and actually automotive applications. But what rod end bearings do is they swivel. So if you were to put a piece through the center of this bearing, what you could really do is swivel it in a lot of different directions. So it's not exactly rotary motion. It could be rotary motion, but it's a different form of movement. So I'm just throwing out a few different examples. Oscillating motion. Again, oscillating motion is a form of rotation, but it may just be many revolutions and then coming back, a part of a revolution and coming back. So oscillating motion is another example. All of these things can be done in sculptures. They can all be done with bearings. This is called a rod end. Yeah, bearing. Here, why don't I've got a few of these, so I'll pass these. Whoops, I'll pass these around. All of these are kind of fun to play with. I have a drawer in my desk in my office with all these samples that people give me. When I'm on a boring phone conversation, I'll pull something out and start to play with it. Oh, yeah, I think that, in other words, I think that is actually a Teflon film lining that provides the slide. But there are graphite axes and anti-friction bushing, oil, and exactly. And that's actually a perfect segue into the first, when I'm actually going to start talking about, well, let me do a couple of quick things first. The other consideration is how is your motion going to be generated? In a lot of cases, like that beautiful sculpture on the table there, it's somebody walking up and turning it. So it's hand motion. And that is certainly what a lot of kinetic sculptures are about. You can see with George Rickey that all of his sculptures are designed, I shouldn't say all of his sculptures, but his sculptures primarily are designed to move in the wind. So they're designed to be outside. Certainly water is a generator of motion. In industry, which is mostly what I'm dealing with, electric motors are what generate motion. So all of these things, how you want the motion generated is something to be considered in your sculptures. And then again, speeds, how fast something is turning, is a critical factor in how you select a bearing. Now, in industry, when we talk about the use of a bearing, we're talking about an electric motor turns at 1,800, a standard electric motor turns at 1,800 RPMs. So it's hard to envision a sculpture that's going to turn at that kind of speed. But when we're talking about the design of bearings and how you select a bearing, that's what initially a lot of bearings, the ball bearings that I'm going to be passing around, are designed to do. So when you think about the speed of bearings, that comes into play somewhat, maybe not as much for sculpture. And then finally, ambient conditions. And again, is it going to be outside? If it's going to be outside, is rust an issue? If rust is an issue, do you want to maybe use stainless steel bearings, or do you want to encapsulate the bearing in such a way that corrosion is not going to be a problem? Contact with moisture, heavy winds. If heavy winds, then you're talking about speeds that you might not have originally designed your sculpture for. When we talk about bearings in industry, really we talk about heat, because the heat that's generated, again, friction equals heat, and it's not just ambient temperature. It can be. If you're putting a bearing in an oven and the oven heats up to 300 degrees, you got to think about what that means. But a lot of it is the heat built up from speed and, you know, in terms of the use of the bearing. But these are all sort of general factors. But let's get much more to the nitty-gritty and talk about a few different kinds of bearings. You know what? We'll get to that. We'll get to the Ricky sculptures in a few more minutes. That's fine. At one point, there was the comment about, oh, you mentioned oil impregnated. There are different kinds of bearings, obviously. Or let me phrase it this way. Two categories of bearings that we talk about. One is a rolling element bearing. It's got something that's creating a rolling component to the bearing. A more simple version is what we would call a sleeve bearing or a bushing. And really, if you envision a piece of nylon tube and you cut a piece of it off, you've created a kind of bearing. It's a sleeve. It may have better anti-friction properties than metal on metal. And as a result, if you have something that's not turning very fast, doesn't have a lot of loads, you're not worried about wear on it, then something like a simple sleeve, it's hard to draw it, but the idea is that you're just talking about a hollow, a sleeve. We call those in the industry bushings. Now, bushings can be made out of a lot of different materials. It can be a little piece of plastic, pivot points on, you know, when you buy something that has a really cheap motor in it, and after a while the motor gets really noisy, and it's like, why did the motor get noisy? It's because instead of putting a rolling element bearing in it, they put a sleeve bearing in it. The sleeve bearing wore over time. It starts to wobble, and it makes noise. It vibrates, it makes noise. Sleeve bearings are very inexpensive, but frankly, if all you're being asked to do is have someone occasionally come up and turn this, then a sleeve bearing might be a really appropriate choice. Now, sleeve bearings can take a lot of different forms. They can take unsophisticated forms, like taking a piece of nylon tube and cutting it, but it can take a form like, I think you mentioned, oil impregnated bushing. Oil impregnated is this, it's actually kind of a fun story. It's a powdered bronze material that is then pressed in a press to form into whatever shape you want. but the powdered metal, the powdered bronze, is impregnated with oil. And the oil is in the material. If you feel it in your hand, it might be a little, it might feel a little oily, but as it's turning, the oil acts as a film that lubricates to keep the metal-to-metal contact from creating friction. How did this come about? There was an engineer at Chrysler who was experimenting with this powdered metal, and they were doing a variety of different things with it, not thinking about impregnating it at all. And this is a true story. He spilled a cup of coffee on this material, and he noticed that the material was absorbing the coffee. And then he made the intellectual leap to say, if we impregnated it with oil instead of coffee, it would act like a lubricant, and we could use it as a material, a bearing material. So the reason I'm mentioning bushings is, in a lot of applications, you don't have to get overly fancy. You can use a sleeve bearing. You can use a bushing. There are also bushings that, in a way, these rod ends I passed around are a form of a bushing. Here's another form of a bushing. This is called a ball bushing because it's still a bushing. You don't really have a rolling element, but it's got a ball in there that swivels, so that these are called ball bushings. And you know, these have a little bit of graphite on them, so they're a little bit dirty. You may hope. They actually make ball bushings that are thrust. These, they make ball bushings, and you know what? I think I can get a picture of one at the end. Remind me, and I'll go to a website and I'll show you. They actually are shaped more flat on the top with, so that as the weight comes on it, these really won't take much thrust, but they do make ball bushings that do take thrust. But let's quickly now move to rolling element bearings. The most common rolling element bearing is a ball bearing. Why a ball bearing? If you have a ball between two pieces of metal, you have, theoretically, a single point of contact. The less contact you have, the less friction. Now, the less loads it will take, but when you're talking about wanting a bearing that moves freely and will actually take high speeds, which is a lot of what we do in the industry, you're talking about using ball bearings because, like I said, you have a single point of contact. If you have another kind of bearing called a roller bearing, well, you know, we can just do it like this. With a roller bearing, you have a line of contact on each side rather than a point of contact. So what does that line do? It gives you the capacity for higher loads, but it gives you more friction, more contact, and as a result, it can't turn as at fast speeds, or theoretically in your applications, it may not turn as freely. But the important thing really at this point about ball bearings, just so we have a little bit of terminology, is you have a few different components. You have an inner race, you have the balls, you have an outer race, and then you have a retainer that keeps the balls evenly spaced. Not all bearings have retainers, but this is sort of your basic bread and butter ball bearing. Now, what will also often happen with a ball bearing like this is that you will then have either a metal plate or a rubber seal over that covers the balls, and before those are installed, lubrication is put in. Primarily grease, sometimes oil. So that then the bearing, those shields or seals are not designed to be removed. They're lubricated for the life of the bearing, but what they do is they keep you from having to worry about lubrication. Metal shields are attached to the outer race and there's just a very small space between the outer race and the inner race. You can't even really, I'm sorry, between the shield and the inner race. You can't really even see it. So that as a result, there is no contact between the shield and the inner race. If there was contact, again, it would cause some friction. It would slow things down. Metal shielded ball bearings are probably a good idea to use if you're thinking about wanting to deal with not having to worry about lubrication, generally encasing and protecting the bearing. There is also a bearing that I'm talking about with rubber seals. Now, sometimes the rubber seals, most of the time, actually make contact with the inner race. The reason you would use a sealed bearing is if it's a really wet environment where you don't want water getting into the bearing. And that in industry, they're used all the time. The problem with them in the use of sculpture is that because the seal makes contact with the inner race, there's a little bit of drag there, and it just takes a little more effort for the bearing to turn. And I think a lot of what people talk about with this stuff is you want your bearings as free turning as possible. So that's just kind of a quick thing about types of bearings. ID is inside diameter. That's the size of the inner race. The size that your shaft needs to be to mount the bearing. OD is outside diameter. That's the size that your housing needs to be in to fit the bearing. Width is the width. Again, I talked about rolling element. Lubrication, we've talked about briefly. Fits and clearance. When you're talking about a bearing turning freely, we can get technical about it, and we can talk about what the internal clearance is in the bearing. What that basically means is how much slop there is between the balls and the inner race. And you want a little bit of slop. In industry, you want slop because as a bearing is turning at 1,800 RPMs or 3,000 RPMs, the inner race is expanding because it's heating. Steel expands with heat. As the inner race expands, the housing can't really expand because the OD can't really expand because it's captured in some kind of housing. The inner race expands. You need to allow some slop so that the bearing will still turn. That's what clearance is. In applications for you folks in sculpture, I think what you really just want to make sure is that you've got a bearing that's loose enough that it's going to turn freely, but not so loose that it's going to slop all over the place. And that's a little bit tricky. I don't think I have to get overly technical about it now. We could talk about it more in a question and answer, or those of you who have experience with this stuff can maybe speak a little bit to how you find that happy medium. Degrees of precision. The other thing we do with bearings is they are made in varying degrees of precision. And just a quick aside, I get a kick out of this. When rollerblading was the big fad, all of a sudden you'd get all these 15-year-old kids who was talking about, well, are you using ABEC 3 or ABEC 7 bearings? And these are terms that we in the bearing industry know and nobody else does. But for a brief period of time, some of this bearing terminology sort of made it out to the general public. What ABEC is industry standard, and then the degree of precision, 1, 3, 5, 7, is how precise they are. And really what we're talking about is how tight they hold the tolerances. Because if the tolerances are held closer, you get more accuracy and concentricity. And concentricity, in a way, if you want something to turn smoothly, the more concentricity you have, the more smoothly it turns. If you want something to turn in a, again, talking about types of motion, if you want something to turn in a jerky way, there's absolutely no reason that you can't use eccentricity as your friend, but again, you have to incorporate that into your bearing design. Generally speaking, we want concentricity in our bearings. Again, so that's just kind of a few of the other things that we talk about. Let's jump to project design requirements. And from that, I'm just going to show you some slides of some of the George Rickey sculptures we have, some of the way he incorporated bearings into his sculptures, and then we'll kind of open it up to general discussion. Again, just go back for 1 second, because I just want to get those terms. Shaft. When you're designing something, it's important to have a shaft that is not going to wobble unless you want it to wobble, that's going to hold the weight that you intend it to hold, that is so not only stiff in terms of the length of the shaft, but you also want a shaft that's held to fairly true tolerances. Those are all important things to make a sculpture turn well. You also have a housing. So in other words, I'll pass these around. The shaft goes into the bearing. These are really big, but ball bearings can start at less than an eighth of an inch shaft or a 3 millimeter shaft and go up from there. But again, shaft requirements, and then the housing that the bearing is going in. If the housing is too loose, the bearing's just going to turn in the housing, and it's not going to act like a bearing. You're going to defeat the purpose of having a bearing. If the housing is too tight, it's going to be hard to get it in there. You may be compressing the outer race of the bearing to a point where, again, it's going to take up some of that internal clearance, and it's going to defeat the purpose of the bearing. Got some little ones here, too, so these are kind of fun to play with. Whoops, kind of like popcorn. Huh? So it's really critical that you think about your shaft, what you're going to use for your shaft, that you think about your housing, what you're going to use for your housing. And let me give you a quick example, and I think this may come up later, but there was a student that couldn't be here today, and Cindy showed me some drawings. And we'll get more to that later. But she was having a problem with her unit moving freely. And she had a bearing that was then attached. I'm sorry, she put her bearing, the bearing actually had a housing attached to it, and some kind of screw mechanism was screwed to the side. And I think the issue was that the housing wasn't staying perpendicular to the shaft. And as a result, because it was cocked a little bit, she wasn't getting the movement. So you need to have a housing. You got to make sure that your bearing is perpendicular to your shaft, and that's really the housing's job. Mounting let me say this. When you get to bigger bearings, and sometimes people will use those of us who are welders love to take a welding torch and weld near a bearing and maybe heat up the bearing to enlarge the inner race so you can slide it on a shaft. That's a bearing distributor's best friend because they have to come back and buy new bearings. Mounting bearings is pretty critical. You want to be careful about how you mount them, but I don't think I need to say a lot about that unless you've got questions later on. Why don't we move to some of the George Rickey slides? George Rickey's sculptures are primarily made of stainless steel. They're primarily, and I'm not a welder, but they are primarily constructed of sheet material that are, I think, spot welded. Does that make sense? So you'll see, for example, a long blade. This piece has 2 long blades. The blades might be 20 feet long, but they might, if you pick them up and carry them, I could certainly take one and carry them around. Maybe a 20-foot blade might only weigh 20 pounds. I don't know. I'm just kind of throwing that out. So with Rickey's sculptures, the issue with bearing design wasn't as much the pure weight, the pure heft. How much radial load are we going to have to worry about? One of the issues was obviously his aesthetic. He wanted a really small, there you go. So you could see he wanted his bearings captured in relatively small enclosures or housings. So one way to do that is to actually stack bearings. If you have one, oh, did I pass that bag around that had all those little bearings? If you take those little bearings, if you look at how narrow they are, if you just have one of those mounted, you've got a lot of chance for wobble, especially if you have a blade or somebody asked me a question about a leaf that they have on a sculpture, and do I size the bearing based on the weight of the leaf or the size of the leaf? If you stack bearings, then you're giving some rigidity, and you're still being able to use it in a fairly small housed cavity. And so a lot of his designs were stacked bearings. Can you go back to that overall thumbnail pages, and I'll have you? Okay. Is that easy to do, or do you want to just cycle through them? That's okay. We could just cycle through them. You know what? Go back. Don't worry about it. Let's just cycle through them. Let's just look at them, because as we look at them, we'll. Yeah. Okay. So here's an example where there are two housings, and the housings are actually the base of these forms that are radiating out, and then the shaft are the two pieces. You could see can you see where I'm talking about the pivot point on those? Again, these may be this big, and the shaft that he's running them on might be a 1-inch shaft. So a lot can be done with small spaces if you don't have weight considerations, et cetera, to offset that. So there's an example of using a cotter pin to keep the entire assembly from sliding out. But again, talking about your example, if there was a small washer, if there were going to be any forces against that cotter pin, if you have a washer that, again, can create some anti-friction, then you keep the assembly from binding with the cotter pin. I don't exactly know what he used there, to be honest. But it's a good example of how he was able to enclose the whole thing. But if you take the cotter pin out, you could slide this whole blade assembly off. Why don't we keep? Again, just a pivot point. I think you're right. I think in that case they are set screws. That's what it looks like. A set screw, machined in will lock. It's just a way of locking something in place. You can actually use, and there was, well, you could do it in a variety. You can, if you lock it to an assembly, the problem with locking a set screw to a shaft is you're undoing, if it's still going to turn, it becomes the friction producing. But a lot of times, if you have an assembly, you can lock the whole assembly. You can lock the housing assembly if the housing is something that could slide in and out. You can lock that. If the rolling element is on the shaft, not where the set collar is, you can then have the bearing doing its bearing thing, and you can lock the set collar on either side of the bearing or on one side of the bearing. On the shaft on one side of the bearing. It'll keep the whole bearing assembly from moving any further up the shaft. So that's in essence what a set collar will do. And I'm going to plead ignorance on this one, but I think it probably, as I look at it, probably is set collar. Sure, keep going. Okay, so this is a weather vane that George Rickey made. There are no bearings in it. Those pieces can move in this direction, and it can also turn. But again, it was more of the principle of bringing a turning, like a top, where you bring the upper part more to a point so that it doesn't have a lot of friction in its turning. And then if you hit the next slide, that's all he did for the pivot points of the vanes themselves. All it is a piece of bent wire. So that's when I say, don't feel like you have to over-design. If a piece of bent wire, if a fishing swivel works, it works. You know, I was looking at some slides of Alexander Calder's mobiles. I suspect he never used a bearing in any of his designs, and he's one of the most famous kinetic sculptors. So I'm talking about bearings here. Whatever works, works. If it happens to be a bearing, great. This is the George Rickey Workshop used to have a Christmas party every year, and they'd invite family and friends, and we would get invited because we were friends of the workshop. And George made party favors one year, which were small sculptures for people, and this is his sculpture. Again, stainless steel, sheet metal, and then if you hit the next slide, the whole sculpture balances on a dimple and a point. So again, it didn't need to have bearings to move. It didn't need, but it provides the kinetic movement. You blow on it, and it moves all over, but it stays in place. It's just balanced properly. So much of it is balanced. Go ahead, keep. This is called one up, one down trapezoid. Again, the shapes are trapezoids. The movement in this sculpture is phenomenal because where the pivot points are on the trapezoids and the angle that they are make it so that they're not moving in a single plane. They're moving in offsetting planes, but they never hit each other. And that's where the engineering goes way beyond my ability. But this is moving. Each of those trapezoids moves on a completely different plane. So sometimes, they'll be in a wind, they'll be offset in incredible ways, but because of the design, they do never touch each other. And again, that's one of the pivot points of one of the trapezoids and my mother's driveway. Why don't we keep going? This is called 4 lines on a T. These are, again, 4 blades. Their rest position is basically horizontal. What he did, and 2 are facing in one direction, and two are pivoting from one direction from my right elbow, 2 are pivoting from my left elbow. They can turn 360 degrees of rotation, but they each turn independently. But when there's no wind, they come to rest like that. He put counterweights. Obviously, it was not just the motion, but the weighting of the lines that were critical in his sculptures. And those lines, you can see, because they're pivoted, so they're cantilevered to such an extent that the cantilevering, rather than your moving point being here and having, just a straight rotation, your moving point is here, so you have a cantilevering, and the counterweight at my elbow was critical. And what he actually did was had a weight that could be adjusted, that is adjustable by a wire, so that if for some reason the weighting were to change, you can actually adjust it. It's not simple, but in essence, you could adjust it in some cases just by moving a screw to a certain extent that moves the counterweight just enough to adjust the balance. So that's the situation with this. Why don't we keep cruising? What happens after that? This came from, just again, 2 lines, kind of interesting with the the setting that it's placed in with all of those electric train tracks, kind of a pose. And again, a sense of mounting, sculpture mounting from the side of the building. These two came from photographs of a catalog I brought. Let's just show a couple of the videos, and then we'll just open it up for questions. I don't want to take... And you'll have to forgive me. I took these videos on a handheld digital camera. In some cases, there's more motion from the camera than there is from the sculptures, but you get the idea. He did not do a lot of the swivel pivoting motion that I talked about with those ball bushings. They are actually moving just in a single, each blade is moving independently in a single rotary, on a single plane. In a high wind, they will go all the way around, but when the wind stops, ultimately they'll end at the rest position that he designed as the rest position. It takes, in this case, like I said, it was a fairly light wind. Even in a light wind, you get that much motion, but in a heavy wind, they'll be really whipping around. But no, the answer to your question is, even though it might look, it's an optical illusion. It's not a swivel. It's a rotation in a single plane. Do you want to field, should I use this as a chance to field questions at the same time that you're looking at these, or comments, or responses to what I've said?
So, what would you recommend for when you've got something that's not balanced? So you've got something with a big arm sticking out, a little circling on one side, a bearing that would take a load at the top apart.
Right, we were talking about that yesterday. I think those moment loads where the weight,
Yeah, I tried doing stuff like that, and there's just too much slop at the end of it. I think there's a weight on the bearing.
right. If this is then enclosed,
Right. That's a lot. That's wide under there, and that's no. What would you like?
well, you know, yeah,
Double bearing.
well, yeah, again, I'm just trying to think. A lot of this is sort of the creative process. Those are some of the challenges that we have. I mean, how much weight are you talking? I mean, what you find is that what's that?
This is theoretical.
Theoretical, but I mean, what you found when you've experimented with it is that you just kind of get that slop.
Piece that you got right now, just, I line it all up and make it all good, all flat, get it all on there, and there's other pieces on top of it, and it kind of,
Yeah.
it's not flat.
And what's
because
in there now?
well, it just has a fair radio bearing, shaft with it, seat.
Okay. Okay.
Still,
Not yet. There's some of, in a case like that, some of what we talk about is the length through bore. The more contact you have, in other words, I was talking about stacking bearings, and the more contact you have between the shaft and the bearing, in essence, the stiffer it becomes, the less it can. And there are things like double row ball bearings that are, in essence, twice the width of a radial bearing, but you don't get, if you stack two bearings, they could move independently. A double row ball bearing wouldn't. So that's a possibility. And the thing about double row ball bearings is a lot of them they're designed in such a way that they're more like that angular contact bearing, so they can actually take some thrust loads also. So that's something you might experiment with. And whereas you're probably familiar with radial bearings and the generic part number has like a 6200 or a 6300. I don't know if you're familiar with that. The double rows would have a 5200 or a 5300. So a 5 in the front of it. On my website, on our website, and at some point Cindy can bring it up, there's a place where it says products. And you can go down on products, and like the first category is bearings. And then we list a bunch of different bearing manufacturers with links to their websites. These are the manufacturers. I checked this morning, and it looks to me like the nearest distributors to Prescott are either Flagstaff or Phoenix. So you're not, unless there's a company that, I mean, you could go to the hardware store and pay a lot of money for a few different sizes of bearings. You can go to your local skateboard shop and you could probably get some bearings, but they're all going to be one particular size. But if you can use that size, you could probably get them pretty cheap because there's a pretty good commercial market. No, our website, that's a link from our website. Let's see, anyway, yeah, I don't remember where. But anyway, okay, there you go. So here's our website. If you go under, and that's www.bdtroy.com. If you click under products, and you click under bearings, we list a bunch of bearing manufacturers, but what I would recommend is that you go to the Consolidated Bearing. Consolidated is actually not a manufacturer, they're an importer, but they have great catalog information in terms of kinds of bearings, dimensions. One of the things that you don't want to do is what often the mechanical engineering students at RPI do when they come over the counter and say, I need a bearing to finish my senior project, and this is what I need. It has to have a bore, an ID of this, and it has to have an OD of that, because I've designed everything else. And guess what? We say, that doesn't exist. What you have to learn, and you probably should have learned it the first day of class, is, find out what exists before you then design around it. So this is a great resource, Consolidated Bearings, and if you type in consolidatedbearings.com, it then links to consbrgs.com. And then you can go to the left-hand side and download PDF files of our catalog. If you click on Deep Groove Ball Bearings, that's going to give you all the different kinds of bearings and dimensional information. The way that's handy is it will tell you, is there a bearing that exists in the sort of general dimensions I'm looking for? I should tell you that a large number of ball bearings, and roller bearing for that matter, series, are metrically manufactured. The technology started in Germany, and so to this day, a lot of bearings are metric in IDOD, a lot of ball bearings. However, there are also inch series ball bearings. But if you get a bucket of bearings and you start looking at them and say, well, wait a second, this isn't fitting right on a 1-inch shaft, there's a good chance it's a 25-millimeter bore. So a good set of calipers is helpful. What you should pay for bearings, that's, let me just put one other plug. I'm an independent bearing distributor. We're a one-branch location. Our competition are New York Stock Exchange type companies with 400 branches, 500 branches nationally. They've got branches in Phoenix. They've probably got branches in Flagstaff. My plug would be, if you can find an independent distributor in those marketplaces, and they exist, it's supporting your local economy in a way that supporting the chains doesn't. Sorry, I just kind of had to put my little independent plug in there. What a bearing should cost, like anything else, it runs the gamut. The bearings that we put in to George Rickey sculptures were almost all stainless steel. They're almost all ABEX 7, which are high precision bearings, because he wanted them to last as long as they could possibly last, and he wanted them to run with as much accuracy as possible. A bearing this big costs $40 if you're using 10 of them in a sculpture. So that's that. I'm not advocating that. I'm just saying that's what he used. Bearings are manufactured in China, they're manufactured in Japan, they're manufactured in Western Europe, Germany, Italy. They're not made in the US very much anymore, believe it or not. There's some kinds of bearings that are, but it's really hard to find the domestic bearing manufacturing market. If it is, it's going mostly towards automotive and not towards industrial bearings that you folks would use. I don't really know the good online shopping places for bearings, although there are a couple of companies like Grainger's. Are you folks familiar with Grainger's? Grainger's might be a reasonable catalog type of company that you can go online. They'll have a whole range of bearings. Their catalog will tell you the dimensions, and you can get them shipped pretty cheaply to you because they're a catalog company. I would suggest a company like Grainger. You might, McMaster Carr, maybe slightly less bearing oriented, but still, it sounds like from experience, yeah. There are definitely bearing distributorships who have e-commerce websites that you can look online and do bearing searches, and they're good at it. You know, we don't go for that sort of, we try and sell bearings as, let me put it this way. Bearings can be sold as, there are certain bearings that can be sold as a commodity. You know, you're making ceiling fans and you want 100,000 of the exact same bearing. Well, if my price is $1 and somebody else's price is 99 cents, and then the next day somebody else's price is 98 cents, and originally I was buying an American bearing and now I'm buying an Italian bearing, but you know what, I can get it from India now and I can only pay 85 cents. Well, now I can get it from China and I pay 70 cents. Well, now, you know, that's what our industry is going through. We at Bearing Distributors, we don't go for that business. We do a lot of value-added services, a lot of design, a lot of helping our customers determine what it is they need, a lot of, well, we would recommend this bearing as a replacement to that. So as a result, we're not very good at sort of that e-commerce type of sales. But I'd be glad, if you want to shoot me an email, I'd be glad at, you know, kind of guiding you through the process. I don't know that I can help. You could see that, you know, Royce had a question that I barely had an answer to, but I threw one idea. I don't know that I can really answer your problems, but I can certainly try. Anything else you want me to cover? Any other questions, comments? Did this meet your expectations of what you were looking for today?